On January 26, 2026, scientists quietly admitted that something from outside our solar system does not behave like anything we understand. Before we dive in, make sure to subscribe and comment where in the world you're watching from. January 26, 2026. That date matters because as of today, scientists are no longer speaking about 3i Atlas with curiosity. They're speaking about it with uncertainty. 3i Atlas is only the third confirmed interstellar object ever detected passing through our solar system. The first was Oumuamua in 2017. The second, 2i Borisov, arrived in 2019. Both were historic. Both challenged assumptions, and both eventually fit, at least loosely, into existing models. 3i Atlas does not. When it was first detected, the classification was routine, an interstellar comet, ice-rich, loosely bound, passively responding to solar heating as it approached the inner solar system. That label carried expectations: predictable outgassing, a measurable dust coma, and a trajectory governed almost entirely by gravity and solar radiation pressure. But within the first week of observation, those expectations began to collapse. Astronomers noticed that 3i Atlas was emitting more heat than models allowed. Not slightly more, significantly more. Its thermal profile did not match an inert body warming under sunlight. At the same time, the chemical signatures in its outgassing were inconsistent. The ratios didn't align with water-dominated sublimation. The distribution was irregular, asymmetric, and difficult to reconcile with known cometary behavior. None of this was dramatic in isolation. In astronomy, noise is common. Instruments misread, data needs calibration. Anomalies are usually artifacts, but this time they didn't go away. Independent observatories confirmed the same readings. Different instruments, different methodologies, same discrepancies. The object's brightness fluctuated in ways that suggested structure, not rotation. Its trajectory showed minor deviations that could not be cleanly attributed to solar pressure. This is where the tone shifted inside the scientific community, not to alarm, not to speculation, but to something far more uncomfortable for scientists: professional confusion, because 3i Atlas was not behaving like a comet, and it was not behaving like anything else we have a category for. It wasn't violating physics, it was doing something worse. It was operating in the gaps between models where explanations exist, but none of them fit cleanly. And when an interstellar object refuses to behave as expected, scientists don't ask what it is yet. They ask a simpler, more troubling question: what assumptions are we getting wrong? To understand why 3i Atlas unsettled scientists, you first have to understand why it wasn't supposed to. Interstellar objects are rare, but they are not mysterious by default. When one enters our solar system, astronomers expect a very specific set of behaviors governed by well-tested physics. These objects are relics, cold, inert bodies ejected from other star systems billions of years ago, drifting through space until gravity briefly captures their path. If the object contains ice, it behaves like a comet. As it approaches the sun, solar radiation heats its surface. Frozen volatiles sublimate, producing a faint coma and sometimes a dust tail. The process is slow, passive, and predictable. Heat in equals heat out. Energy conservation holds. Nothing surprising. Its trajectory is equally unremarkable. Gravity dominates. Sunlight adds a slight push through radiation pressure, gently nudging the object away from the sun. Astronomers can model this with extreme precision. Deviations, when they occur, are small and explainable. This is why 2i Borisov, the second interstellar visitor, caused excitement but not concern. It behaved exactly like a comet should. It confirmed what scientists hoped. Interstellar space produces familiar objects, different origin, same rules. 3i Atlas was expected to follow that script. It should have brightened smoothly as it warmed. Its outgassing should have increased gradually and symmetrically. Its motion should have been boring in the best possible way, predictable enough to calculate months in advance. This kind of boring is what scientists want. It means the models work. It means the universe is still playing by the rules we understand. That's why interstellar interstellar objects are usually treated as scientific bonuses, not existential questions. They help refine theories of planetary formation. They offer chemical snapshots of other star systems, and then they leave. No alarms, no emergency meetings, no redirections of billion-dollar telescopes. So when astronomers say Three-Eye Atlas should have been boring, they don't mean unimportant. They mean it should have quietly reinforced everything we already know. Instead, it did something far more disruptive. It behaved just enough like a comet to be classified as one, while consistently refusing to act like one in practice. And that is when scientists stopped treating Three-Eye Atlas as a visitor and started treating it as a problem. The first signs that something was wrong with Three-Eye Atlas didn't arrive as a single shock. They arrived as a sequence of small disagreements with expectation, the kind scientists are trained to tolerate. The earliest deviation was thermal. As Three-Eye Atlas moved closer to the Sun, infrared observations showed it heating up faster than the models predicted, not dramatically at first, but consistently. A comet at that distance should warm at a rate governed by solar input alone, yet Three-Eye Atlas was radiating excess heat, enough to place it well outside the error margins of standard thermal models. The immediate assumption was calibration error. Instruments drift, data gets noisy, so teams recalibrated. The numbers didn't change. Then came the chemistry. Spectroscopic analysis of the object's outgassing revealed molecular ratios that didn't align with water-dominated ice sublimation. Instead of a smooth, predictable release of volatiles, the emissions were irregular, both in timing and composition. Some compounds appeared in concentrations too high for passive heating. Others appeared briefly, then vanished. This wasn't how frozen ice behaves when it warms. It looked uneven, structured. Again, none of this was alarming on its own. Comets are messy, their surfaces are heterogeneous, localized jets can distort readings. Scientists have catalogued hundreds of odd comets before, but then the spectral signatures complicated things further. Certain absorption lines did not correspond cleanly to known ices, silicates, or simple carbon compounds. The data suggested organized molecular structures more complex than rock, less random than dust. Still ambiguous, but persistent. Different observatories using different instruments reported the same mismatches. This is where dismissal stopped working, because each anomaly, thermal excess, irregular chemistry, spectral inconsistency could be explained individually. Together they formed a pattern, and patterns are what scientists pay attention to. Within days, major observatories began reallocating time, not because anyone suspected danger, but because curiosity had crossed into concern. JWST adjusted its observation schedule. ALMA increased monitoring frequency. Ground-based telescopes refined tracking. Three-Eye Atlas had not broken the laws of physics. It had done something more unsettling. It had exposed gaps between those laws, spaces where explanations were possible but increasingly strained. And once multiple independent teams reach that conclusion, the question is no longer whether the data is wrong. It's whether the models are. Up to this point, every irregularity in Three-Eye Atlas could be filed under complexity, uncomfortable, yes, but still manageable. That changed when its motion was analyzed. Trajectory is where astronomy becomes unforgiving. Objects either follow gravity or there is a reason they don't. As Three-Eye Atlas passed through the inner solar system, ESA's Gaia spacecraft began reporting subtle but consistent deviations in its path. The numbers were small, fractions of a degree, but they mattered because the direction of the deviation was wrong. In most cases, when an object deviates from a gravitational trajectory, the explanation is straightforward. Solar radiation pressure. Photons from the sun impart momentum, gently pushing small bodies outward. This effect has been measured, modeled, and confirmed countless times. It always acts away from the sun. Three-Eye Atlas Atlas was doing the opposite. Gaia's data showed a non-gravitational acceleration component directed partially against solar radiation pressure. Not enough to suggest propulsion, not large enough to trigger alarms, but large enough that no passive explanation fit cleanly. Scientists tested the usual alternatives. Outgassing jets, the chemistry didn't support sustained thrust, asymmetric mass loss, the observed emissions were too weak, dust tails, insufficient density. Every correction reduced the discrepancy but never eliminated it. This is the moment when Oumuamua re-entered the conversation. For years, physicists, including Michio Kaku, had pointed out that Oumuamua exhibited a similar anomaly, acceleration without visible outgassing. That question was never fully resolved. Many researchers accepted provisional explanations and moved on. 3I Atlas didn't allow that luxury. Here was a second interstellar object showing non-gravitational acceleration that resisted conventional causes, not identical to Oumuamua but uncomfortably familiar. Enough to suggest this was not an isolated fluke. Michio Kaku has often warned that when anomalies repeat, they stop being anomalies. They become data, and this data implied something deeply problematic. Either interstellar objects behave in ways we fundamentally misunderstand, or our models of small body dynamics are incomplete in ways we have not yet accounted for. Neither option is reassuring, because once motion itself becomes unpredictable, scientists stop asking what the object is made of and start asking what else it might be capable of. Up to this point, the problems posed by 3I Atlas were physical: heat, motion, trajectory, all difficult but still confined to the language of mechanics. That changed when scientists examined its chemistry more closely. Comets are chemically simple. Their outgassing is dominated by water vapor, carbon monoxide, carbon dioxide, methane, small stable molecules that form easily in cold environments. Occasionally, you'll find simple organic compounds, short carbon chains, alcohols, or basic hydrocarbons. Nothing unexpected. 3I Atlas did not follow that pattern. High-resolution spectroscopy revealed molecular structures that went well beyond simple volatiles. These were not random fragments broken off by radiation or heat. They were organized, repeating, structured in ways that suggested stability rather than decay. Scientists detected complex organic molecules, multi-bonded carbon frameworks that require specific formation conditions. Some of these compounds are known precursors in laboratory studies of biochemistry. Not life, not organisms, but the kinds of structures that, on Earth, sit one step away from biological function. This is where discomfort set in, because interstellar space is hostile to complexity. Radiation breaks bonds. Time erodes structure. Over millions of years, complexity trends downward, not up. Random debris simplifies, it does not organize itself. Yet these molecules appeared intact. Even more unsettling was their distribution. Instead of being scattered evenly, the compounds appeared in ratios that suggested selective preservation or selective formation. Neither explanation fits cleanly within current comet chemistry models. Statistically, this matters. The probability of detecting a single complex organic molecule in a cometary plume is low, but not extraordinary. The probability of detecting multiple organized compounds in consistent ratios from an interstellar object is far smaller. Combine that with the earlier thermal and trajectory anomalies, and the odds compress rapidly. Still, scientists resisted interpretation. No claims of biology were made. No language of intent entered the discussion. Official briefings emphasized caution. Extraordinary claims require extraordinary evidence. But privately, the conversation had shifted, because chemistry does not lie in the same way motion sometimes can. Molecular bonds tell a history. They record environments, processes, and survival conditions, and the chemistry of 3I Atlas was telling scientists something unsettling, not about what it was, but about what kinds of things it might have been capable of carrying. For the first time, 3I Atlas was no longer just a physical anomaly, it was a chemical one. Until this moment, 3I Atlas was strange, but distant, a problem for models, not for people. That distinction disappeared with the ejection event. At first, it looked routine. Instruments monitoring 3I Atlas detected a small mass separation, something breaking away from the main body. Comets shed material all the time. Ice fractures, dust jets, surface layers peel off under thermal stress. But within minutes, scientists realized this was different. The velocity of the ejected material was far too high. Natural outgassing produces separation speeds measured in tens of meters per second. Under extreme conditions, perhaps a few hundred. What was recorded here exceeded those limits by a wide margin. The material didn't drift away. It was expelled, cleanly, directionally, with force inconsistent with passive sublimation. That triggered immediate reconstruction. Teams at NASA and ESA replayed the event frame by frame, synchronizing data from ground-based telescopes, space-based infrared sensors, and deep space tracking arrays. Timing, vector, velocity, all recalculated independently. And then came the realization that changed the conversation entirely. The trajectory intersected Earth, not approximately, not statistically, precisely. If the separation had occurred hours earlier, the material would have missed Earth by hundreds of thousands of kilometers. Hours later, the same. But the ejection happened inside a narrow window, one that aligned the object's path directly with our planet. This is where the language in internal briefings shifted. 3I Atlas was no longer discussed solely as an interstellar anomaly. The focus moved to the separated mass, its speed, its direction, its destination. Because once scientists confirmed Earth intersection, the object stopped being abstract. It became an incoming event. Follow-up calculations refined the projection. Atmospheric entry was now not just possible, but likely. The margin of error shrank with every update. Radar tracking improved. Optical confirmation followed. No conclusions were announced publicly. Caution dominated official statements, but internally the implications were clear. Something had left 3I Atlas with more energy than nature should provide, and it was coming here. At that moment, the central question stopped being, why does this object behave strangely? It became something far more immediate. What exactly is on its way to Earth, and are we prepared for it to arrive? At this stage, confusion is not a failure of science, it is the correct response. By the time the ejected material from 3I Atlas was fully characterized, researchers were facing contradictions that did not belong to a single field. They crossed physics, chemistry and biology, and each discipline arrived at the same conclusion. The observations could not be reconciled with existing models. Start with radiation. Interstellar space is saturated with high-energy particles capable of breaking molecular bonds over time. Complex organic structures do not survive intact for millions of years. They fragment, degrade, and simplify. Yet the molecular signatures associated with the ejected material showed coherence. Bonds preserved, structures organized, patterns intact. Then there is energy. The object displayed thermal emissions and internal activity that exceeded what passive solar heating could explain. No known chemical process in an inert body accounts for sustained energy output at those levels without rapid depletion. There was no visible fuel source, no decay signature, and yet the signal persisted. Finally, there is structure. Spectral data suggested organized molecular arrangements, neither chaotic debris nor simple compounds. This is the most difficult contradiction of all. Random processes produce randomness. Over time, structure dissolves. What scientists were seeing implied the opposite. Each of these problems has proposed explanations. Radiation shielding, exotic chemistry, unusual geometry. Scientists explored them all. None solved everything. And this is where Michio Kaku's framework becomes important. Kaku has long argued that when an observation violates one model, science adjusts. When it violates two, caution increases. But when it violates multiple independent models simultaneously, thermal, chemical, and dynamical, science must stop and reassess its assumptions. That is the position researchers now find themselves in. No one is claiming certainty, no one is invoking conclusions beyond the data, but the data itself is demanding something unusual: a pause, a reset, a willingness to admit that the current explanatory toolkit may be incomplete. This is not panic, it is intellectual discomfort, because the most unsettling possibility is not that 3i Atlas represents something extraordinary, but that it is revealing how narrow our understanding has been all along. And when scientists say they are confused, what they mean is this: the universe is no longer answering the questions we are asking in the way we expected it to. Throughout this entire sequence of events, one voice has remained notably careful. That voice belongs to physicist Michio Kaku. Kaku has never claimed that 3i Atlas represents alien life or extraterrestrial technology. In fact, he has gone out of his way to reject premature conclusions. But caution in science does not mean denial. It means knowing when probabilities stop being informative. Physicists live in a universe filled with unlikely events. Rare does not mean impossible. Improbable does not mean meaningful. Cosmic coincidences happen constantly across billions of galaxies. The key distinction, as Kaku often explains, is between something that is merely unlikely and something that is statistically absurd. An unlikely event strains intuition but remains within expectation. A statistically absurd event violates multiple probability thresholds simultaneously. It forces scientists to ask whether randomness is still a valid explanation. This is where 3i Atlas becomes uncomfortable. Thermal anomalies alone could be chance. Unusual chemistry alone could be an outlier. Non-gravitational acceleration alone could be modeling error. But when these factors converge independently, repeatedly, and across different instruments, the combined probability collapses. Kaku has emphasized this point for years, particularly when discussing Oumuamua. One unexplained object can be dismissed. Two begin to suggest a category. Three demand attention. 3i Atlas is not drifting towards certainty. It is drifting toward improbability so extreme that scientists must at least consider alternatives they would prefer to avoid. That does not mean intent is proven. It means intent can no longer be ruled out. This is a subtle but critical shift. Science does not leap to extraordinary conclusions. It expands the hypothesis space when conventional explanations fail. That expansion is uncomfortable but necessary. Kaku frames it this way: when data refuses to fit the model, you do not discard the data, you question the model. And that is where the community now stands. 3i Atlas has not answered the question of what it is, but it has forced physicists to confront a more difficult one. At what point does coincidence stop being scientific skepticism and start becoming scientific denial? For now, restraint remains, but the boundary is moving, and scientists can feel it. There is a question that does not appear in official statements. It is not written into press releases or highlighted in conference briefings, but it exists quietly, persistently, in every serious discussion surrounding 3i Atlas. If this was not random, then what was it? Scientists are trained to avoid framing questions in ways that invite speculation. Precision matters, language matters, and so publicly the focus remains on measurements, error bars, and alternative explanations. That is not avoidance, it is discipline. Privately, however, the implications are unavoidable. Planetary science operates under a fundamental assumption: incoming material is inert. Meteorites are rocks. Cometary debris is frozen chemistry. Even Martian samples, if ever returned, are expected to be ancient and inactive. That is what planetary protection protocols are designed for: dead material. 3i Atlas challenges that assumption. The anomalies observed so far do not confirm activity, intent, or design, but they do point to complexity that resists passive explanations. And that is where the discomfort lies, because existing containment frameworks are not built for unknown systems that may be structured, adaptive, or reactive. This does not mean danger. It means uncertainty. Scientists are not afraid of discovery. They are afraid of overconfidence. History has taught them that misjudging unfamiliar systems especially biological ones, can have consequences far beyond the lab. That is why restraint dominates the response. No one is claiming this object was sent. No one is asserting purpose. But the possibility space has widened, and with it the responsibility to proceed carefully. What happens if the material behaves unpredictably? What if it responds to its environment in ways we do not anticipate? What if our assumptions about containment are simply wrong? These are not sensational questions. They are operational ones, and that is what makes them uncomfortable. The fear is not of invasion or catastrophe. The fear is of misinterpretation, of assuming familiarity where none exists. So scientists are doing what they always do when faced with the unknown: slowing down, double-checking, and refusing to say more than the data allows. But silence does not mean ignorance. It means the question is too important to answer casually. And for now, the most honest thing science can say about 3I Atlas is this: we do not yet know what we are dealing with, and pretending otherwise would be the real mistake. Regardless of how the story of 3I Atlas ultimately resolves, one fact is already clear. This moment matters, not because we have answers, but because we have reached the limits of our current ones. Science does not advance in smooth, predictable lines. It moves in jumps, driven by moments when observations no longer fit the frameworks built to explain them. Most discoveries refine what we already know. Rarely, something arrives that forces us to question the foundation itself. 3I Atlas sits at that boundary. If future analysis reveals a natural explanation, an exotic chemistry, a misunderstood physical process, a new class of interstellar object, that outcome would not diminish its importance. It would expand our understanding of what the universe can produce. It would rewrite models, update textbooks, and sharpen the tools we use to interpret reality. And if it does not, then the significance grows even larger, because history shows that science progresses not by clinging to certainty, but by confronting uncertainty honestly. From heliocentrism to quantum mechanics, every major shift began with confusion. Professionals admitting that the universe was behaving in ways they could not yet explain. This is one of those moments. 3I Atlas has not delivered conclusions. It has delivered questions. Questions about chemistry, physics, probability, and the assumptions we quietly rely on when we think we understand the cosmos. That is not a failure of knowledge. It is its engine. The temptation in moments like this is fear. Fear of the unknown. Fear of implications we are not ready to face. But fear has never been what moves science forward. Curiosity does. Curiosity is what built the telescopes that detected 3I Atlas. Curiosity is what drove scientists to follow the data even when it became uncomfortable. And curiosity is what will carry this investigation forward carefully, patiently, and without rushing to conclusions. Whatever 3I Atlas turns out to be, it has already done something remarkable. It has reminded us that the universe is under no obligation to be simple, and that when our explanations fail, the correct response is not panic, but wonder, because history is written not when we confirm what we already believe, but when we discover how much more there is to learn. What came from 3I Atlas may turn out to be natural, or it may force science to redraw its boundaries entirely. Either way, this is one of those rare moments where the universe reminds us how much we still don't know. If you found this breakdown valuable, subscribe for more Science Explained without hype, and comment below. Do you think 3I Atlas will eventually have a conventional explanation, or are we witnessing the start of something new?